Okay, so chi-squared test for independence. First of all, let's talk about what's the difference. We're going to kind of review a little bit and then jump into the new and go through this fairly quickly because it's pretty much the same thing that we've done. But chi-squared goodness of fit. What's the difference between goodness of fit and just a chi-squared test? Goodness of fit has one variable. Chi-squared tests have two variables. Now, the other thing, within the two variables, we have two different types of tests that we are going to do within the two variables. One, the homogeneity that we talked about yesterday. What is a chi-squared test for homogeneity? Multiple populations. Okay, and we're comparing population A to population B to C, so on and so forth. The chi-squared test for independence is only going to be one population, and we're testing two variables within that one population. So let's go backwards, clear back to chapter 1 and chapter 5. What does it mean for there to be an association between two variables? One affects the other. That's the easiest way to remember that. Knowing the outcome, or one variable affects the other. They're related to each other. There's an association. And when we did this back in chapter 1, we looked at conditional distributions. That's where we first introduced conditional distributions. So it's fitting that a chi-squared test for independence goes back to conditional distributions like we talked about on Wednesday. What does it mean for two variables to be independent? They don't affect each other. We want to put that a little bit more technical, so we're going to go with this definition. Knowing the outcome of one does not change the outcome of the other. So when we test this chi-squared test for independence, we're testing to see if there is or is not an association between those two variables. We're testing to see if one variable is independent of the other variable. Here's the thing that tricks kids up a lot of times. Association and independence are antonyms of each other. If there is an association, they are not independent. If there is not an association, they are independent. Okay, so they're antonyms of each other, and that kind of confuses kids sometimes when we start talking through some of the language of this. So, how is a test of homogeneity different than a test of independence? There's one key difference to really focus in on. Homogeneity has two populations, and we're looking at one variable among those populations. Independence has one population, and we're looking at two variables among that one population. Okay, so my hypotheses will look like this. The null hypothesis for a test of independence is there is not an association between whatever variables you're measuring, between blank and blank, in the population of interest. In other words, my null hypothesis, there is not an association between these two variables. So what does that mean is true about those two variables? They're independent. So then the alternative hypothesis would be there is an association between blank and blank in the population of interest. In other words, They are not independent. And really, that's the only difference between homogeneity and independence. It's just in what you're checking or what you're testing. All the other math, all the other calculator, all the other work with it is all the exact same as what we did on Wednesday. It's just this initial idea of why we're running this chi-squared test. When we did it before, we were comparing multiple populations. When we're doing it now, we're testing to see if the variables are independent of each other. So, real quickly, kind of showing you an example of this. I want everybody to take your dominant hand, your right hand if you're right-handed, your left hand if you're left-handed, and raise it up, just flat up in the air, and fingers together. I want you to see if your ring finger is longer or your index finger is longer.
My ring finger is longer. If your index finger is longer, then you're weird.
How many of you have a longer ring finger?
Oh wait, ring?
Longer ring finger. Look around the room.
What if they're the same? Oh wait,
If they're the same, then it's not longer, so just you don't raise your hand. Look around the room. Is there any association between anything that you see looking around the room?
If you're fat, then you don't.
Is there any association between the people you see raising their hand?
no, right
You have a ring.
Mostly male. If you have a longer ring finger, raise your hand. I'm sorry, I said the wrong one. Longer index finger. Longer index finger, raise your hand.
Estrogen.
What do you notice?
Estrogen.
Mostly girls, right? So, we want to put this to a test. We want to test, is there a relationship between gender and which finger is the longest secondary finger? Your middle finger is obviously the longest finger, right? I don't want to make you all flip me off, so we're not going to tell you to show me that. But between your secondary fingers, is there an association between them? In other words, we've said this a lot. Does knowing somebody has a longer ring finger make them more likely to be male? We don't know for sure. According to what we just did, it kind of does, right? Does somebody that has a longer index finger make them more likely to be female? Based off of what we saw, probably. And we can also flip that the other way around. Does knowing they're female make them more likely to have a longer index finger? And does knowing that somebody's a male make them more likely to have a longer ring finger? So, when we did this back in chapter 5, we used conditional probabilities, right? The probability of being male has to be the same as the probability of being male given to have a longer ring finger. You guys remember that? So we were just testing one category when we did that conditional distribution test back in chapter 5. This chi-squared test for independence tests all of them together, doing all of those conditional probabilities by finding the expected counts and comparing them all at once. So that's what this chi-squared test is doing and how it's beneficial for us. Now, the math to this. The expected counts. The generic formula for that is n times p. We modified that to be row times column divided by total. And what do we want for those expected counts? We want them all to be greater than or equal to 5. So when we did this the other day, where were those expected counts stored that we could actually go look at them after we were done? They were stored in matrix B. The test statistic. What test statistic do we use for a chi-squared test? Chi-squared. And what's the formula for chi-squared? It's the sum of all the observed minus expecteds. That's a horrible E. Squared over expected. Okay, this is all review. It's all the same stuff we did before, right? Degrees of freedom is number of rows minus 1 times the number of columns minus 1. And finally, the conditions for a test of independence. They are the same, except one small thing. What's the one small difference for the conditions for independence versus homogeneity? It's the main difference between the two, but in the conditions part, it's one small difference. What'd you say?
One population.
We only have one population that we have to test the 10% condition with. We only have to test that 10% condition one time for a test on independence instead of all the populations for homogeneity.
Wait, I'm so confused. I was like, are you sure we're doing the JCCCCCCC review hours 1, 2, 3, July,
Okay, turn in your notes to this problem, the Arizona Daily Star. We're skipping the ring finger problem because we kind of already talked about it. We're not going to do it. I want to do a different one instead when we work all the way through that. So skip over to this one. This problem addresses some of those.
I'm going to get this bread.
Addresses some of those theoretical or conceptual understandings with this test. So Arizona Daily Star in 2009 had some data that included the following table. Suppose you decided you want to analyze this data using a chi-squared test. Can we use a chi-squared test on this data? Well, first of all, let's talk about age. This is a good review. This is the first question on the JUCO test last year, is this example A right here. What's the difference between categorical and quantitative data? Okay, good. Age. Age is one of those rare variables that can be split into both categorical and quantitative. Why? How in this problem did they force age to be a categorical variable? They put it into ranges. They made it into groups and they broke it into ranges, so now we have it be a categorical variable. So age is one of those rare variables that can be both categorical and quantitative. If we make it into age ranges, it becomes categorical. Zach, take your hat off for me, please.
Oh, a minute and 32 seconds.
Only because I was trying to finish a thought. All right. Now, letter B. How do we know that a goodness of fit test is not appropriate here? Multiple variables. What are my two variables that we have in this problem? Age and use. On network use, right? Social networking use. Those are my two variables. So goodness of fit test will not work. We need to know if we're going to do a homogeneity test or an independence test. So letter C and letter D ask you this question of how do you know basically, or how could you gather this data so that this could be a homogeneity test versus being an independence test. This is kind of that conceptual understanding. How well do you know the difference between homogeneity and independence? So if we were wanting to do a chi-square test for homogeneity, how could we gather the data for this problem to make sure that it is a homogeneity test? How can we gather the data on this problem? Or how could the Arizona Daily Star have gathered the data on this problem to make sure that it is a homogeneity test? Bella, what did you say? I think you're on the right track with what you said. If I heard you right, what did you say? Good. We went online to social media network sites and we found a random sample of 386 people from an online social networking group of some form and asked them their age. And then we went somewhere else and found 698 people that are not on social networks and asked them their age.
Does anyone have a Band-Aid?
We broke it into two separate populations thereby making it a homogeneity test.
I need two.
Is that the only way that we were able to do this as a homogeneity
I
test?
gotta wash my hands first. It's been in my mouth. Look at that. Do you see that? Is that gross? It hurts so bad. Owie.
How else? How else could we have done this? Tanner?
Separate the populations to the age groups and then ask them if they use it or don't.
Good. We could have intentionally sought out 183 18 to 24-year-olds and asked them, do you use social networks, yes or no? Then we could have intentionally sought out a random sample of 25 to 34-year-olds. A whole different group of people, right? Because when we do this, we have to sample from different populations, not the same population. So ask 221 people that are 25 to 34, do you use social networking, yes or no? Now, shifting gears on that, changing it up a little bit. This one's a little bit more difficult. How could we have done this so that it is a test for independence? What's the key here?
Just found like a large group of people, asked them their age and whether they use. We asked them both questions.
Good. We went and got one large sample of 1,084 people. We went to the mall and asked people as they were going through the mall. We went to, as somebody said first, we went to their church and stood outside the doors of their church and asked people, how old are you and do you use social networking? Okay? The key here is what? All 1,084 have to come from the same place, the same group, one population. Okay? So independence is one population, one sample. Everybody gets asked both questions. Homogeneity is separating it out into two separate populations, or in this case, 6 separate populations, and asking them one single question.
So, for the homogeneity, you're saying the two populations would be like one from school and one from church, and then asking them the question?
No, you can't do it that way because that doesn't separate it out into these populations. If you're doing homogeneity, your populations have to be, this is one population and this is one population. So you have to find, your population has to be people who are online social network users, and then ask them their age. Your second population has to be people who are not online social networks, and ask them their age. Does that make sense? Okay. Okay, so kind of making sure we understand the difference between homogeneity and independence there. Now, last problem here that I want to work through with you and show you this process and put it all together. Researchers surveyed 100 students on which superpower you would most like to have. Which one would you most like to have? The ability to fly, the ability to be invisible, or some other superpower? Okay, so it says compare the distribution of gender for these 3 superpowers. We want to see, is there a relationship between gender and which type of superpower they prefer? Looking at the data, what do you think?
Yes.
What do you think is the relationship?
That women don't like flying.
Women don't like flying? Or more women want to be invisible than men. Okay? Looks like fewer women want to fly than men, and more women want to be invisible than men. So we're going to test that and see if those differences are a significant enough difference to believe that there is a relationship between them or that there is an association between them. Okay, so what type of test am I doing? Okay, this is going to be a chi-squared test for independence. So what will my null hypothesis be? Real close. We have to say it. What's our population?
Among men and women.
Population of 100 students.
But we don't want to do it from the sample. Because the sample is just what we're using to test it. But what are we testing? We're testing among all students.
Do I put among all students?
You can. You can also just write among students.
I know. There is an association between gender and super coerce among students.
So we have our hypotheses. Now let's go check our conditions. First condition, was it random? Well, all they told us here was that researchers surveyed 100 students. So what we're going to say is that the survey should have been random. Somehow say that the survey should be random. Now, if you were going to question this test, what's the first thing that you would go question? Whether or not that survey was gathered randomly. Okay, so then the next condition is 10% condition. So what's my sample size in this? 100 is less than 10% of what's my population? All students. And finally, large counts. We save for later. We're not going to do that yet because we have to go get that from our calculator. Remember, though, I will ask you this. It's on the quiz for Monday. It's on the test for Friday. How many females do we expect to say other? How many females do we expect to say other? So we'd have 52 here, 18 here, 100 here. So females, let's say other, we would take 52 times 18 over 100. So it should be like 9 point something. As part of the large counts check, we're doing one component of the large counts condition to make sure you know how to do it, and then we're going to let the calculator do it. What'd you get? 9.36. So we expect 9.36 females to say they prefer the superpower other. We observed 8. The other question that will show up with that is calculate the chi-squared component for that. So how do we calculate the chi-squared component for females that say other? If I ask you to calculate this part of it by hand, not if, when, the chi-squared component for females that say other, how do we do that? Okay, so the individual chi-squared component, you have to know how to do that as well. Where, yeah, Lily?
For large counts, do we have to do just like a sample of one of the expected for every problem?
Not for every problem, only if I specifically ask you. Okay, where do we store our data at? So we're going to go into our matrix menu. And we're going to edit matrix A. rows by columns. So this one will be 3 by 2. Okay, so we have our data put into matrix A, 2 by 3, 2 rows, 3 columns. What do we do to actually run our tests then? Stat, tests, chi-squared test, observed in matrix A. We're going to store the expected in matrix B, and we're going to calculate that value. What again is my p-value on this one? Beware of this. It's a really small value. Don't forget to look over here to the far right. You can't have a p-value over 1, so we know that the p-value could not be 7.7. Okay, so 0.0007 is my p-value with 2 degrees of freedom. So going back over here, I'm going to go ahead and record that information. My chi-squared value was 14.33. I had 2 degrees of freedom, and my p-value was 0.1237. Don't finish the problem yet, though, until you have actually checked the expected counts. Because if you go finish the problem and do your interpretation and all that, and then you go back and look at the expected counts and it fails the expected counts condition, you just spent a whole lot of extra time doing all that for no reason. So before you go ahead and make your interpretation and your conclusion, let's go ahead and go back to our calculator and check our expected counts. How do we see our expected counts? We go into matrix B. So we're going to go over to edit. Edit is the best place to see it. Instead of displaying it, we want to edit it. We're not going to actually change any values, but it shows them the easiest on our screen when we do it this way. So, are all of my expected counts at least 5? Is it good enough to just say that? No. You have to go back over here and show that. 19.76 and 18.24. Thank you. So all those values are greater than 5. The large counts condition is met. So because all my conditions met, now these values down below are valid. We can go ahead and sketch our curve. Chi-squared value 14.33 with that p-value is going to be way over here to the right with a really small area. My chi-squared value 14.33. What can we conclude? Because 0.0007 is less than alpha equal to 0.05, we can reject the null. By the way, don't forget to give your evidence. I saw a lot of people not giving evidence. That's like going into a courtroom, giving your opening argument and giving your closing argument and walking out. Are you going to win very many cases that way? No. This is your evidence. You have to give your evidence. Okay, so because all of this evidence that we showed right above here is so significant, we can reject the null. What do we have? We have enough evidence. Good. We believe there is an association between gender and superpower preference among students. So we got a significant result. We rejected the null. What do we have to do? We have to do our follow-up analysis. I intentionally wanted to do this one because I wanted to show you how to do the follow-up analysis part of this on the calculator. So, what's the purpose of a follow-up analysis? Why do we do a follow-up analysis? If the problem tells you to, yeah, that's when we do it. But what's the purpose of it? Why are we doing this? What are we trying to find out by doing a follow-up analysis? Which variable impacted the data the most? Which variable impacted our decision the most? Which one was the most significant difference? So when we do this follow-up analysis, what are we looking at on our calculator? I shared this with you guys yesterday or Wednesday. The biggest difference, but how do we find the differences when we're doing the matrices on our calculator? It does not give it to you like the contribution list. What do we subtract? Other way around, but yeah. Matrix A minus matrix B. Observed minus expected. So on the calculator, we're going to go back to our main screen. We're going to go into matrix A minus matrix B. Second matrix A minus second matrix B, and hit enter. What do these numbers represent? What do these values represent?
Do you write those down? You have to write these down.
Answer my question first. These are the differences between my observed and expected. How much each category affected our chi-squared value. Okay, now, why are they some negative and some positive in this case? Underrepresented, overrepresented. But on the contributions list, they were all positive because they were squared. Remember, matrices. We can't do this squared because matrix multiplication doesn't work like we want it to in that case. Okay, so we have to look at these and realize, and now in this case, because there was only two populations or two variables here, they're going to be exactly opposite of each other because one's above it, the other's got to be below it from what we expect. So when there's only two in one category, this will happen. When we have three or more in each category, then you start to see the numbers vary a lot more. So if you scroll to the right, you can see all of the categories again. So which variable impacted, or which category impacted my chi-squared value the most? Which one was the biggest discrepancy between males and females? Invisibility. And how was that impacted? So my follow-up analysis. Invisibility had the biggest impact. And what else do we have to include with that? The direction. So with females being overrepresented, overrepresented in our sample. You don't have to. The follow-up analysis is more just, hey, what's going on with this? Which one was weird? It's not necessarily a numbers thing. It's just more of an interpretation thing. Where did that come from? Well, we had 32 females that were observed, and we only expected 22 females. So females way overrepresented how many of them said they wanted to be invisible than what we expected. So there is a significant difference. Females, knowing they're female makes them way more likely to say invisibility than males.
Why do we say females were overrepresented versus males?
You could say either way. It doesn't matter on that. Yep, that's a good question.
Oh my god, it's so funny.
Lily? Okay.
And it doesn't tell you to do a follow-up analysis. What are the conditions for it?
The condition for following up analysis, I think I heard Jake say it. Anytime we reject the null, you want to do a follow-up analysis. Do you need to wear a hat? Because Zach has a hat to make sure your head doesn't explode with pride. Okay, so anytime we reject the null, we want to do a follow-up analysis because we want to see, yeah, it was significant. What caused it to be significant? It should just be a natural curiosity that follows to make you want to do a follow-up analysis. All right.